Good evening everyone. Yeah, so we'll be discussing chemical bonding in this particular session. Okay, so first what we are going to study in this, so like what exactly, like how many types of chemical bonds are there, what exactly chemical bond, and next what is this Lewis approach. Okay, then next Fazan's rule, valence bond theory, these one after other we'll be discussing here. The first one is, so tell me why like what exactly chemical bond means. See, we have, yeah, it is like a force of attraction between the atoms. Force may be any type, that force of attraction may be different types here. Okay, so that holds them together, that holds atom together to make a bond, like to form a molecule or a compound. Okay, and why this chemical bond formation is taking place? See, everything in the like in the nature happens to gain stability. So for what purpose? To gain stability. Even these chemical reactions are also taking because of to gain stability, to attain stability. So why chemical bond formation takes place? To attain stability. Okay, so bond formation associated with stability. Now the attaining or the atoms, here we are discussing about atoms now. So attaining of this stability will be takes place by chemical reactions. So during this chemical reaction, what happens? The electron, like transfer of electron takes place, like gaining of electron, losing of electrons, these kind of things are going to happen here. Okay, so now an element has tendency to occupy inert gas configuration. What do we mean by inert gas configuration? Like we have noble gases now, like helium, neon, argon, krypton, radon, like xenon, these things are there now. So those configurations. So the element has a tendency to occupy inert gas configuration. If they occupy that 18th group element configuration, all the orbitals in that particular element will be fully filled. Therefore, it is considered as stable. Okay, so due to that reason, they will always try to occupy this inert gas configuration. Now attaining of this inert gas configuration is possible either by transfer of electrons, okay, or by mutual sharing of electrons, or by donation of pi electrons or lone pair electrons to the other system. For example, here first one, transfer of electrons we are writing. Now sodium I am giving you. What is the atomic number of sodium? 11. So what is its electronic configuration? 2s, 1s2, 2s2, 2p6, 1s2, 2s2, 2p6 and 3s1. Okay, so now see, this is the extra electron we have. If I remove this extra electron, now see, all the orbitals are fully filled inside. Right now, it means during the chemical reactions, what happens is alkali metals like sodium will lose this one electron and becomes unipositive, like Na plus. Right now, so how many electrons it is losing? 1 electron. Now how many are there? So 10 electrons are there with this. Now 10 electrons is nothing but noble gas configuration. What is that noble gas? Neon gas configuration. Okay, so it is having neon gas configuration which is stable here. Right now, so now similar to this, now I have some other element. Now for example, chloride atom I have. What I am taking? Chlorine atom I am taking. So its atomic number is 17. Now argon atomic number is 18. Okay, it means how many electrons are required to attain this argon configuration? 1. Right now, so now whenever it is combining with sodium, from sodium it will take 1 electron. Okay, like alkali metals, from alkali metals it will take 1 electron and become chloride ion. Okay, so now see what happening. So from sodium atom to chlorine atom, electron transfer is taking place. Yes or no? So it is happens by transfer of electrons. Okay, both are gaining stability by transfer of electrons. Okay, so this is a kind of transformation that leads to attain the stability by those respective atoms forming respective ions. Okay, and mutual sharing of electrons. For example, I have chlorine atom and another chlorine atom here I have. Okay, how many electrons are there with the chlorine? 17th group now, it means 7 valence electrons are there. Okay, so 7 means you just put 7 dots like this. One more is required now. So what I am making is one more dot I am keeping like this. 7 are there. Here also you put 7 dots. Okay. Now tell me how many electrons are required to fulfill or to gain its 8 electron octet configuration. One more electron is required. Therefore, both of them required one electron now. So now they mutually understand each other and share this electron with each other. So it becomes a chlorine bond like this. How many electrons are there around the chlorine now? See, 6 here, and this is mutually shared now, 7, and this is also belongs to both, 8. Both of them are happy now, both of them got octet configuration. So this is happening by mutual sharing of electrons. Okay, next. Donation of lone pair electrons. So sometimes it is also possible by donation of lone pair. We are saying that as day 2 bond, we will discuss that later. Okay, and here types of bonds we have. One is ionic bond or electrovalent bond. How this is formed? By transfer of electron from one element to other element, like we have seen in the case of sodium chloride formation. From sodium to chlorine atom, electron transfer taking place. Right now, next, what about this covalent bond? So this is formed by mutual sharing of electrons, both atoms like chlorine atom sharing mutually. Okay, next we have coordinate covalent bond. It means for bond formation, how many electrons are required? 2 electrons are required. So both of that electrons are donated by one atom itself. For example, I am having ammonia here, simple understanding, and I have BF3 here. Okay, so now BF3 have only 6 electrons with one vacant orbital. Okay, boron trifluoride here, and nitrogen is like ammonia, nitrogen contain non-bonding electron, this lone pair electrons. So this will be donated into this vacant orbital. Therefore, initially it has only 6. By donation of these 2 electrons, now it is having 8. So both of them are getting octet configuration, 8 electronic configuration right now. So that is what we will see in the case of coordinate bond. Okay, next we have metallic bond, that is possible between the 2 metals, and hydrogen bond, this is special case, we will discuss at the end with a special discussion, very important. And van der Waals bond, this we will discuss at the end. Okay, right. Now first, in order to explain this structure or the compound formations, we have first approach here Lewis dot structure, or in order to explain the structures, this is the first model here we have. What is that? Lewis dot structure. So in this Lewis dot structure, Lewis consider the valency electrons of the atom represented. The valency electrons means, for example, I am writing carbon electronic configuration as 1s2, tell me, 1s2, 2s2, 2p2. Okay, 6 electrons are there, like this you should write. So now during the chemical reactions, only these valency bonded valency shell electrons are participating. It means out of these 6 electrons, how many are taking part in the bond formation? 4 electrons only. Okay, it means these valency electrons are considered as dots around this carbon atom. It means how many dots I should place for this carbon? 4 dots, like carbon 1 dot, 2, 3, 4 dots, like this. Okay, so now similarly for hydrogen atomic number 1. So therefore how many electrons are there? 1s1. This is the only valence electron it has. Therefore, in order to attain 8 electrons or octet configuration, carbon can form how many bonds with this kind of atoms, like 1s1, 4 now. So one hydrogen atom here, 1 electron, another here, other one here, and one more here. So it will make 1 bond like this. Therefore carbon got octet configuration now. 8 electrons are there, each bond 2 electrons, 4 bonds, 8 electrons are there. So 8 electron species, all the neon gas configuration it has now. Okay, all p orbital and s orbitals are fully filled. Okay, so this is a stable electronic configuration, and we are seeing this 8 electron as octet configuration. Okay, and now hydrogen having how many electrons? Each hydrogen, see, 1 electron here, 1 electron here. So 2 electrons. In the case of hydrogen atom, we should call it as duplet. What is that? Duplet. In other cases, it will be 8 electron octet. Okay, remember this. Okay. Yeah, is this clear? 2 electrons, duplet, octet. Okay, in case of carbon, you should consider octet. In all other cases, in case of hydrogen, you consider duplet. That's it. Okay. Now what he told is, Lewis dot structure, when he is proposing these structures, he told that those compounds are stable which has this 8 electronic configuration or this octet electronic configuration in their molecules or ions. Okay, this is what he considered and given. See, this is what, this is nothing but methane molecule, CH4. Yes or no? This is methane only, na? Like this. So he also given for other something like ammonia. If I take nitrogen, how many valence electrons are there? 5. So like 2s2, 2p, 3. Okay, so you put 5 dots like this, like this. Okay, and I am saying ammonia, right? So ammonia means how many hydrogens are there? 3. So like this we have 3 hydrogens. Okay, therefore we got this. Now look how many electrons are there around the nitrogen in this ammonia? 3 from bonds, 3 to the 6 and here 2, total 8. So octet configuration it has. Now what about hydrogen? Doublet, that is also stable, right now. So like this he considered. Now there are some compounds which are existing and they are not following this octet rule, but as per him what he told, compounds which are following octet rule are stable and existing. Okay, so for example here if I consider these are the limitations. So BCl3 or BF3, if I consider boron atomic number is 5. How many electrons are there? Valency 1s2, 2s2, 2p, 1. So valency electrons are 3. So now you put 3 dots around the boron. 1, 2, 3 dots I am placing. Okay, how many chlorines are there? 3. So like this if you put 3 chlorines, now tell me how many electrons around the boron you are seeing in this molecule? 1, 2, 3, 4, 5, 6. Only 6 electrons are there right now, but having 6 electrons which is lesser than the octet. Right now we know octet 8 electron containing compounds are stable right now, but it is having only 6 electrons only, but it is also existing and being stable, which was not explained by him. And what is the reason behind this was not explained. Therefore it is considered as limitation of Lewis dot structure. Okay, so what we should say, if electron count is less than 8, you should say them as incomplete octet. What is that? Incomplete octet. Deficient also, electron deficient species. Okay, okay, is this clear? Now look at here. So what are the limitations? First limitation is there are some compounds having incomplete octet in the central atom. Okay, but that does not have complete octet but still stable, something like BF3, BCl3 like that. Okay, and next one, some compounds are there having expanded octet. It means more than 8. One is incomplete, another one is expanded. For example, I am saying SF6 and PCl5. So how many electrons are there in this case? Simple, phosphorus, valence electrons, nitrogen, phosphorus. Nitrogen family means 5 valence electrons. Surrounding atoms are also 5. So total 10 electrons are there. So it means greater than 8 now. So expanded. And here 6 valence electrons in sulfur and 6 surrounding atoms means each one. So 12. This is also expanded octet now. So was not explained about these things. Okay, how they are existing and stable. Okay, therefore they are considered as limitations here. And you know, see, BCl3 actually having structure of trigonal planar. It means trigonal planar means like a triangle if you consider like this. Like this. See, it is looking like a triangle now in a plane. Yeah. So this is the structure of BCl3. But he is not explained the structures like what is the exact geometry of the molecules. For example, in the case of methane, we have like given like this. So it is something like looking like a square, like having 90 degrees like this. But this is actually incorrect. If you experimentally, if you observe what exact structure of methane looks like, is it have a tetrahedral geometry. What is that? So like carbon, if you want to imagine it in a board or if you want to write, so just take this is above the plane and this is something like below the plane, hydrogen atom, and two are within the plane, like this you should understand. Okay, yeah. So what is the angle between the two lines here? Bonds 109 degrees 28 minutes. Okay, or 109.5 degrees, you remember. Okay, so this is the angle, but if you look at here, it is just a 90 degrees, which is highly unstable here. So he was unable to explain the geometry and structure in the Lewis dot explanation. Okay, yeah. And what he told, compounds will attain like noble gas configuration, therefore they are stable, they are saying. Okay, they won't show reactions, but there are some noble gases. For example, xenon is a noble gas, no? Yes or no? So noble gas means it should be stable, it should not show any reactions right now, but xenon also forming some compounds. It means xenon also showing reactivity. It means like compounds like it is forming like XeF2 and XeF4, this kind of compounds are existing. So which is not explained. See, xenon, which is a noble gas, but still forms some compounds. But as per him, what he told, noble gases are highly stable, therefore other compounds always try to attain this noble gas configuration, which is also a drawback here. So these are the drawbacks that should be remembered. Okay, yeah. And what is the last point I told you? He gives no idea about molecular shape of the compound. Okay. Yeah. So those who are in the comment box, yeah, please try to listen it properly, and you can raise the doubts here in the chat box. Yeah, next let us move forward. So tell me, in which compound expanded octet of central atom is present? Expanded octet is present in which of the compound given? PCl5. Just now I have given it now. How many electrons are there in this? 10 electrons, which means greater than 8. Here BF3 is having how many electrons? 6. So I can say this is incomplete right now. So our answer B is perfect. And what about H2? It is duplet. What about CCl4? Octet configuration for central atom. Okay, only option 2. Next, we'll discuss about ionic bond. Yeah, we'll discuss about ionic bond. Here, ionic bond is formed by complete transfer of one or more electrons from valence shell of one atom to the valence shell of other atom. For example, here I have best representation. See, this is a sodium. Atomic number of sodium we have. Atomic number of sodium is 11 right now. It means how many valence electrons we have here? 2s2 we are writing, like 1s2, 2s2, 2p6. So these electrons are inner electrons, they won't participate here. Only this 3s1 electron is there now. This is the valence electron. Okay, so now the complete transfer of this valence electron, which is highlighted here, will transfer from here to here for the chlorine. Therefore we will get sodium cation and chloride anion. Therefore it results to form a ionic compound. See, now cation, anion, both opposite charges now. So between the oppositely charged ions, electrostatic force of attraction will be there. So results to form ionic compound or ionic bond. So what do we mean by ionic bond? It is a electrostatic force of attraction between two oppositely charged ions. Okay, that's it. Okay, now what are the factors influencing the formation of ionic compound? Okay, so one is ionization energy, electron affinity and lattice energy. So what exactly ionization energy means? We studied now. So tell me, what is ionization energy? See, for example, we have sodium cation, sodium atom. So in order to convert into sodium cation, what we are making, atom is converting to cation. So during this process you are removing one electron now. So this process is called ionization energy. Okay, and what about electron affinity? For example, chlorine atom we have and we are converting into chloride ion. So during this process we are adding one electron. Okay, so now the species having less ionization energy. It means what? The species, the metal atom or the atom which having tendency to give the electron easily will form ionic compound readily. It means I have something like sodium, potassium, rubidium, like this I have. So which element will give electron easily? That is what we need to check. Rubidium. Why? Because it has low ionization energy. So element should have lower ionization energy and greater electron affinity, okay, and more lattice energy. So what is this lattice energy means? Lattice energy means the amount of energy released when two oppositely charged ions are coming together to form 1 mole of ionic compound. So more amount of energy released, that is what more lattice energy for that particular substance. Okay. So now they will ask which are the arrange the following in their lattice energy order. For example, lattice energy, you just take this formula or you just remember this, lattice energy will be more if the charges are more. Charges are more, like Q1, Q2 means charge of cation and charge of anion, and here I am writing R square. What is that R? Size. Okay, like R square means cation, anion sizes are there, those sizes you remember. Okay, so when is organic? Okay, I will start organic after around some 15 days after. Okay, yeah. So look at here. So charge should be more and size should be small, therefore lattice energy will be more. See, directly proportional to charges and inversely proportional to size. Now I am giving you something like NaCl and CCl, KCl. So tell me, lattice energy will be more in which case? See, chloride ion size is same in both cases, right now, and charge is also same here and here, right now. Yeah. Now what is the other thing we need to consider? Look at the charge, like size of cations, which is smaller size? Size of sodium or size of potassium? Down the group, what happens to the size? Increases. Okay. So it means sodium cation is smaller size, therefore radius will be small in first case. So small radius, more. So NaCl having more lattice energy than KCl. Like that you should understand. Okay, is that clear? Right. Let us move forward. So what are the characters for these ionic compounds we can have? Yeah. So they are hard, brittle and crystalline. You just observe the rock salt, the table salt at your home, how it will be crystals now and hard. Right now, yeah. So hard, brittle and crystalline, and they have high boiling and melting points, and they are polar in nature. Right now they are polar now, yeah. So since they are polar, the polar compounds soluble in polar solvents. What do we mean by polar? Like there should be polarities, like poles should be generated in the given compound. For example, I am saying water is a polar molecule. It means due to the electronegativity difference between hydrogen and oxygen, it become partial positive charge here, and more electronegative oxygen should be partial negative charge. So this kind of poles are generated now, so I can consider it as a polar solvent. So now the polar compounds, generally ionic compounds will have more solubility in this type of solvents, like polar solvents, like dissolves, like you remember. Okay, and ionic compounds are very less soluble or non-soluble in non-polar compounds. If I want to soluble this compound, if I dissolve this in CCl4, it won't get dissolved, it won't get soluble in this. Why? Because it is a non-polar compound. Okay, do you remember this point? Yes. Next, they soluble in polar solvents such as water, and insoluble in non-polar solvents like CCl4, benzene, these things. Okay. Now ionic compounds are very good conductors of electricity in their molten state and in the aqueous state. So what do we mean by molten state? You just boil it, I mean just melt it first. Okay, the crystals are there now, melt it first. So when you melt it, you will get the respective solution, right? That is what its molten form we are saying. Okay, yeah. So in the molten form and in the solution, it means you just take some salt. If you take pure water, it is a very bad or poor conductor of electricity. but if you add salt to it, yeah, it will conduct electricity. Why it is? Because now the charge can be carried by the free ions, like cation we have and anion we have. So now these are the ions, free ions are there present in that solution to carry the charge, electricity. Therefore that makes it to be good conductors. Okay, yeah. Next, covalent bond. So covalent bond is formed by mutual sharing of electrons. Okay, so now, okay, so for example what I can say, it is formed by mutual sharing of electrons. Okay, and next, this mutual sharing of electrons I will tell you, like hydrogen atoms we have taken. How many electrons are there with the hydrogen atom? 1s1. Right now 1 electron here, 1 electron here. Therefore see, if I give one more electron to this, the s orbital will get fully filled. Therefore this atom also required and this one also required 1 electron each. So they mutually share this 1 electron and makes hydrogen molecule. And tell me, in the nature hydrogen exists in molecular form, not in the atomic form. Okay, this is a stable state. Okay, right. Now similarly halogens also be having molecular state, not the atomic state. Now what about oxygen atom? Having how many valence electrons? 6 now. So put 6 dots like this and take one more oxygen atom also, and now tell me how many are required to gain 8 electronic configuration? 2 more are required. So now this fellow also required 2 and this one also. So he will share 2 electrons to this and like this. So how many electrons it become? Both of them 88. Both are stable, octet. Is that clear? Right. Okay, so mutually shared. Now you know, this is a term we need to learn here, new term. The number of bonds present between 2 atoms are how many here? 1. So its bond order is 1. Okay, now between these 2 atoms? 2. So its bond order is 2. Okay, remember this, we will talk about this later. Okay, next. Now what I am saying is covalent character in ionic bonds. So we have seen ionic bonds, covalent bonds till now. Okay, so now ionic bonds are formed by, how they are forming? Transfer of electrons. After transfer of electron we are having cation and anion. Between them electrostatic force is present. This is what we have studied. Okay, but in the nature there is no compound which is 100% ionic. There should be at least some amount of covalent character in every ionic compound. Okay, so how can we understand this in a better way? So look at here, sodium losing 1 electron to chlorine and forming sodium cation and chloride anion. After this, just look at here, sodium is having what? Now sodium having positive charge on it now. This is the nucleus of sodium, you can consider like positive charge. And this is the nucleus of chlorine atom, and this is the electron cloud of chlorine atom, and this is the electron cloud of sodium. Okay, so now what happens is, since it has more positive charge, what it will do, it will try to attract the electrons if anything present nearby it. So now chloride ion is having electron cloud now, expanded electron cloud, right now. So therefore what it will do, this positive charge will drag that electrons towards itself. So it means nothing but it is mutually sharing only now. The electron cloud from here is slightly dragged by Na place. It means slightly chloride ion is sharing this electron pair with the electron cloud with the sodium ion, right now. So can we say it as covalent nature? Right. See, something like this. See, slight dragging, this gummy kind of thing, slightly it is dragging towards what? Na place, right now. So that makes it to be having some covalent character. So identify this, which are the following compound contain both ionic and covalent bond. Identify. All of these are. So first tell me, between NaOH, what type of bond it is? Here Na plus, see, always remember, if there is alkali metal, that always if alkali metal is in any of the compound in the combined state, always it will be +1 oxidation state. Okay, it will be +1. Now this species should have -1. Okay, so between oxygen and hydrogen, covalent bond. So it contains both ionic as well as covalent. Okay, what about Na2SO4? Between S and O, covalent. Between this Na2 and sulfate ion, ionic. Okay, and between KCN, between C and N, covalent. Between this one, K plus. So all of this. Is this clear? Yeah. Next. What I told you, there is no compound 100% ionic, there will be some covalent nature. So now how much amount or what is a like how can we decide, like for example, what is the amount or order of the covalent character in the given ionic compounds? How can we decide the order? That is given, the explanation is given by these rules, Fazan's rules. Okay. So what I am saying, Fazan's rules helps us to decide the covalent nature in the ionic compounds. So what are these Fazan's rules first? There are 5 rules to be remembered. There are 5 rules to remember in order to decide the ionic character in the covalent compounds. So what are these 5 rules? So first one, see, we know in ionic compounds there will be cation and anion. So that cation should be smaller size and it has more positive charge. See, always remember, I am writing atom A and its cation A plus and its one more cation A plus 2, dipositive. Now tell me in this, tell me the order of these compounds, of these ions, which is smaller size. Always remember, more the positive charge on that particular atom, smaller will be the size. Okay, this is smaller and then next like this. Okay, so smaller size cation and it should contain more positive charge. Cation should be satisfy these rules, 2 rules first, and next when it comes to anion, anion should contain large size, okay, and more negative charge on it. So why? Because see, if the cation contains small size and more positive charge, now it has more ability to drag that that cation has more ability to drag the bonded electrons from the electron cloud of anion. For example, here we have this. Yeah, look at this. I am writing anion. So remember, this is small size indicates what? Cation, and large size indicates anion. Why large size I am indicating with larger size, like anion indicating with larger size? No, it is not like that. The electron cloud here will be expanded in the case of anion. For example, I am writing B is an atom and B minus is an anion of that atom. Now tell me, where do we have more electrons? B minus. It means its electron cloud will be bigger, expanded, therefore size will look larger. Like this you can understand. Now if this cation drags a bonded like this valence electrons of anion more effectively towards itself, I can say the polarizing power of this cation is more. So cation should have more polarizing power and anion should have more polarizability. It means ability to get polarized by this cation. So how can we decide that ability of anion? If the anion size is large, that large anion size is possible when it has more negative charge. Okay, size should be large for anion, charge should be more on anion. So that makes it to be have more polarizability and polarizing power of cation. So if these two are there, then that compound will be having more covalent nature. Okay, now this will be more clear when you look into the examples. Look at here, I am writing this example, and you know this is a very simple easy topic. You can answer without wasting your time in the exam and can be understood by everyone. Please follow here. See, I have CaCl2 and I have NaCl. So tell me which is having, otherwise we will take MgCl2. So tell me which is having covalent nature, more covalent nature out of these two. Huh? How you are saying that MgCl2? See, we have like what is the anion here? Chloride ion, chloride ion. So we cannot decide our answer with respect to anion because both anions are same here. What about our cation here? Na plus 2 and Mg plus 2. So now more positive charge. So it means more polarizability for polarizing power for Mg plus 2. That makes it to be show more covalent nature. Therefore, which is more covalent out of these two? That's it. Okay. So now if covalent nature increases, solubility decreases. We know ionic compounds are readily soluble. For example, you just take water and you just take pinch of salt as well as pinch of sugar. Okay, try to add them. So where you will see more solubility? Salt case, because it is ionic, readily soluble. Right now? So I can say sugar has more covalent nature now, so its solubility is relatively less when I compare with the ionic compounds. Okay, like this you just for generalized example for understanding purpose I am giving. Okay, so now based on this we have lot of questions. If you followed this, just look at here. From moving from BaCl to BeCl2. So BaCl2, this group, which group element these elements are? Which group chlorides are these? Beryllium, magnesium, calcium, strontium, barium belongs to second group, right now? Second group. So now tell me what happens from beryllium to magnesium, magnesium to calcium, strontium, barium we have. So now what about their sizes? Down the group size increases. So all of them are having same charge now. See, chlorides are -1 here in all the cases, and strontium, all these metals are +2. So which is having small size? Down the group cation size decreases. Okay, so which is having small size cation? Beryllium. Therefore that compound will be more covalent, more polarizing power for this, that makes it to be more covalent. So covalent nature will be something like this. Right now? So if I ask solubility, opposite to this. Right now? So more covalent nature, low solubility. That's it. Okay, clear now? Yeah. And next you can also explain their melting point orders also. So more covalent nature, lower melting points. Means ionic compounds has more. Once again.
More solubility, more melting point.
See, more ionic compound it has more solubility and more melting point. Or more covalent nature, low solubility, low melting, like that. Okay, yeah. So this will be the order for covalent nature, and opposite will be the order for solubility as well as melting point. Okay, is that clear? See, melting point decreases with increase in covalent character. These are the applications. Okay, and next solubility decreases in polar solvents and increases in non-polar solvents as covalent nature increases. So more covalent nature, lower solubility of that particular salt in water, in the polar solvents I can say. Okay, now tell me which is correct out of these four options. Yes, answer fast. Huh. Correct statement they are saying. FeCl3 is more covalent than FeCl3. FeCl2 is more covalent than FeCl3. No. What about this? FeCl3, because more oxidation state here, Fe plus 3 and Fe plus 2. Which is having more polarizing power? Plus 3. Therefore, it makes it to be more covalent. So, this is correct. Next one? Equally covalent? No. Next? No. Next, what about this one? See, this is a previous year question. You should answer this now. Hydrates are there. So, hydrates means here beryllium will be in the plus 2. Alkali metals, like metals are in, like this is Ba, you can take. Not B only. Beryllium, calcium, strontium, barium here we have plus 2, and hydrogen is in minus charge, hydrate. All of them are hydrate, minus anion size is same. Now look at the cation sizes. Charge is also same. So down the group what happens to their size? Increases. So small size, more covalent nature. So which is having more covalent nature? Beryllium hydrate will be having more covalent nature. And what they are asking? Ionic character. So opposite to that. So more covalent for beryllium hydrate. Okay, it means least ionic character it has. So least ionic character here we have and here we have. After that, more covalent nature for calcium. So lesser ionic character. So here we have. So this will be your answer. Clear now? Easy? Yeah. Let us move forward. Answer this. Fast. A greater covalent character for an ionic bond if small size cation are more positive charge in the case of cation, and anion large size anion, and what more negative charge. Right now these are the criteria. Okay, now as per that, small size cation greater covalent character, small size cation perfect. Okay, large size of cation no. Next, small size anion, large size cation no. So what is a suitable answer? Only one. Okay, now before going to this, I have one more question here. So look at here, I have NaCl and CuCl. Out of these two, which is having more covalent nature? Out of these two, answer. Which is having more covalent nature? How can we say CuCl is more covalent here?
Left to right.
Yeah. So look at here. What is the anion here? We have chloride. So we cannot answer with respect to anion size or anion. We should answer only with respect to cations here. So cation is sodium cation here and Cu plus cation here. Right now. So now out of these two, this is having what is the valence electronic configuration, like 2s2, 2p6 and 3s0 now, as one electron is removed. And for what about this? It is having like 3d9, 3d10, 4s0. Right now, and inside we have this one like 3s2, 3p6 electronic configuration. Now total how many electrons are there here? Count.
15.
6 to 8 plus 10, 18 electron configuration now. What about this? 8 electron configuration. So if we have 8 electron configuration, you should say octet configuration or inert gas configuration. What is it? Inert gas configuration we are using. Inert gas configuration we are seeing right now. So but here when you have 18 electrons, you should say pseudo inert gas configuration. What is that? So whenever you have an element or ion with inert gas, other one with pseudo inert. So pseudo inert gas configuration containing metal have more polarizing power. So more polarizing power means more covalent. Okay, so that makes it more covalent. Okay, so therefore which is having more covalent out of these two? CuCl. That's it. This is how you need to answer. Therefore solubility will be less for CuCl and more for that's it, NaCl. Okay, yeah, this is about the session. In the next session we will study about valency bond theory and other things. Okay, right. Any doubts are there? No. If no doubts, we can wind up.